Hi there, this is the bonus video that explains how the log laws come to be. And I'm glad you're here because it means that you appreciate, as well as I do, that understanding how laws work makes it easier for you to understand how to apply them. So we're going to go through them one at a time, and I'll be doing a bit of groundwork to start with. And what you'll notice is that there is a definite correlation between the log laws and what they look like and a similar power rule, I think. So let's get into it. And I'm starting off with this first one here, which is that log base A of m times n is equal to log base A m plus log base A n. Notice that same base, same base, same base here. Okay, so the startup is to say let m equal a to the power of p for some value of p. We don't know what p is, but there's some value of p. And we'll let n equal a to the power of q for some value of q. I've just picked p and q. I could have used x and y or two other variables, but it's just saying there's got to be some number out there. So what does that mean? It means that p is equal to log base am, and q is equal to log base a n. Again, for some value p, for some value q. So what about it? Well, let's have a look at m times n. M multiplied by n would be a to the power of p multiplied by a to the power of q, because that's how we defined it, which is equal to a to the power of p times p plus q. Okay, using our index laws this time, our exponent laws, which says that we add powers together if it's got the same base. So we've got mn is equal to a to the power of p plus q. Moving on to slide 2. Okay, now let's use our basic log definition to work out what that expression could be translated as. So we put the power on the left, p plus q. So therefore, p plus q must equal log base a of mn. Okay, can you see how we're now getting closer to the law that we had in the first place? But what is P and Q? Well, we defined that over here, that P must be log base AM and Q must be log base AN by the way we defined it. So we end up with, instead of P, I write log base AM. Instead of Q, I write log base AN, and I have log base AMN. So it's in reverse, I know, left to right, but that's the law, done. And we could use a similar sort of level of logic to work out this as well. So we start off with let A equal, start that again. Let P equal, let M equal A to the power of P, and N equal A to the power of Q. For some P and Q we haven't worked out, we won't need to in the end. Okay, and then we say that P is equal to log base AM. That's a basic definition of a log. And Q is equal to log base AN. Great. But this time we'll go M divided by M divided by N is equal to A to the power of P over A to the power of Q. And that equals A to the power of P minus Q, like so. Alrighty, so now we'll use the basic definition of a log in order to figure out what's happening next. So that means we'd have P minus Q is equal to log base A of M over N, like so. P we defined as log base AM, Q as log base AN, so we end up with log base AM instead of P minus log base AN instead of Q equals log base A of M over N, and we're done. So not too bad, huh? This third one here might be worth pausing the video and seeing if you can work it out yourself. It's not as tricky as perhaps it looks. There's a few ways of trying to solve this, but if you just consider M being a whole number, a whole positive number, and then think about law number 1, maybe you can figure it out. So pause the video and maybe think about that. Okay, let's see. I hope you were able to work it out yourself, but in case you didn't, something like this would work as an okay definition. Okay, so I'm going to go down here so that we've got a bit more room. X to the power of m really means x times x times x times x. And we do this, m times. Okay, so that means by that law 1, we've got log base ax plus log base ax plus all the way to log base ax. And we've done that, m times. So if I've added exactly the same if I've added exactly the same number up m times, I've got m lots of that number. So that means it must be equal to m log base a x. And we're done. All right. In slides 6, 7, and 8, we've just got some further results. I more or less went through them in the other video, but let's have a look at them again. Log base a. Well, remembering our basic definitions, a to the power of what is going to equal a. So since a to the power of 1 is equal to a, log base a must equal 1. It's as simple as that. Log base a1, similar logic, since a to the power of what is equal to 1? 0. Anything to the power of 0 is equal to 1. Since a to the power of 0 equals 1, log base a1 is equal to 0. And number 8 here, well, you could use law 3 in order to solve that problem fairly readily, I think. But another way of looking at it is like this. Log base a x to the power of negative 1 is equal to log base a 1 on x, okay, which is equal to log base a1 minus log base a of x. And then if you look at that the slide 7, you can see that log base a1 is 0. So that it gets removed, and I'm left with negative log base a x. So that's an important outcome. It means that if you've got negative log base a of x, it can be written as a positive log by making the power negative. So I'm just doing this off the top of my head, so I'm hoping this will work. But if you've got something like negative log base 3 of 7 equals log base 3 of 2x, and you were asked to solve that, you can't solve it directly or very easily in this format that it's in there. But if I bring the negative power in to go log base 3 of 7 to the negative 1 equals log base 3 2x, I can use, similar to equating coefficients or equating exponents, I can equate my logs there and say, therefore, 2x equals 7 to the negative 1, 2x equals 1/7, and x equals 1/14. So there's a bonus little example there about how to solve a problem where you've got a negative on the outside there. It's not the only way to solve it, but it's kind of just trying to explain why that result is particularly useful. Okay, I'll leave this video here.